So good morning, everyone. Before I started, I just wanted to make sure you're all aware that this is a talk about DLLs, right? Like there's people all over the conference talking about very interesting things right now, but we're going to talk about DLLs. All right, just I want to give you the opportunity to, leave if you want to. So actually, the talk is titled Everything You Ever Wanted to Know About DLLs, but I need to amend that a little bit. So it's actually going to be a few things you probably didn't want to know about DLLs. If I was to cover everything there is to know about them, it would take me a whole conference worth of sessions. So this is going to be sort of an introduction to how DLLs work. We're going to touch on a lot of things. We're not going into a ton of detail in the talk. So my name is James McNellis. I'm a senior engineer on the Windows debuggers team, so I work on WinDBG. You may have been at our talk yesterday. We announced and released some brand new time travel or reverse debugging tools for Windows, which are very exciting. You should go check them out. Most importantly on this slide, you can see my Twitter handle. You should all go and follow me. That would also be great. So we've got a lot of things that I'd like to talk about here. Some of the things that toward the end we may cut depending on time. We'll have to see. So we're going to start by looking at how you build a DLL, how to use a DLL in a program, look at what's inside of a DLL. We'll look at explicit and implicit linking, what happens when you load a DLL, how to diagnose DLL load failures, various ways to specify what a DLL exports. We'll look at data exports, delay loading, C++ threads, and then DLL hell. And then maybe there will be time for questions. So what we're not going to talk about dynamic libraries or shared objects on other platforms. So obviously many other platforms have shared libraries of various forms. I've been programming on Windows for a long time now, so I don't have that familiarity that I'd need to give a talk on that. And also, I only have an hour, so I have to constrain what I'm going to talk about. This is CppCon, so we're not going to talk about .NET. We're going to talk about native, DLLs that have native code in them. We're not going to focus on any other kinds of DLLs or uses of DLLs, like resource DLLs as well. And so we'll mention a lot of things that we won't discuss in depth, but I've tried to put enough information on the slides that if you search for things, you'll be able to find them quite easily using Bing or, if you prefer, Google. So what and why? So a DLL is a dynamic link library. That's what those letters stand for. So it's a library that contains code and data, just like a static library. But it can be loaded dynamically at runtime. So you don't actually have to link it into your program when you start. When you actually build it, you can choose whether or not to load it at runtime. Additionally, it can be shared or reused between multiple programs. So a static library can also be shared between multiple programs because you could link it into, for example, 20 programs. But then if you distribute those programs, well, you have 20 copies of that code or data or whatever you've linked from that on disk. So DLLs, you only need to have one copy of it. You don't need to have multiple copies. So most normal DLLs have a DLL file extension. You don't actually have to have a DLL file extension. It could be a .text extension. It will work just as well. Well, some things will work just as well. So why use DLLs? So the biggest advantage that I already touched on is multiple programs can share code and data without each programming having its own copy. So this can reduce disk space usage because your XEs are smaller. You have this code that's actually shared. It can also reduce memory usage because if you have DLLs that are loaded into many different processes, all of the read-only pages of those DLLs can generally be shared between the multiple processes. You can reduce overall memory usage across the system, even if you may be increasing slightly your own virtual address space usage within a process. You can defer decision of whether to load functionality until runtime, so perhaps you may not always need some functionality, like for example, if you write a print driver, you don't want to load your print driver into every single process regardless of whether it's printing or not. You want to load it when you actually need to go and print. Or perhaps you want to support other kinds of open-ended extensibility like plugins. There's also maintainability benefits, so componentization is enabled by DLLs. If you only work on one little part of your project, you can keep rebuilding just your one DLL. You don't have to rebuild the entire thing necessarily. It can improve serviceability because, if, let's say there's a critical security bug in some of your code, if it's in a static library, you actually have to go and rebuild every single thing that's linked that bug into the program. Whereas with a DLL, you can just rebuild the DLL, redistribute it, and everyone picks up the fixes. And then finally, there's some improved maintainability, basically for the same reason. There's also disadvantages, so it certainly makes software distribution more complicated, right? If you build everything into a single XE, well, you can just give that to people and run it, and it works happily. But with DLLs, there's multiple files. Maybe you have to install some of them differently, so it can be a bit more complex. There's increased potential for incompatibilities. I'm sure many people here have had to deal with DLL hell or DLL hell-like issues. And then it's a small thing. It's impossible to optimize code across DLL boundaries, or at least with today's tooling. So if you statically link code in, you can actually do whole program optimization, link time code generation to optimize across different source files. But with DLLs, there's actually a hard boundary. Every call into a DLL is an indirect call. So enough talking. Let's build a little DLL. So I'm going to build a DLL named hello.dll. We're just basically all of my slides. We're just going to use the command line. I'm going to have all the commands you need. Most of the command output will be shown. Sometimes I've trimmed things down just to fit them on the slides to focus on individual things. But you should be able to take all these commands, all the sample code, and just copy and paste it and do the same thing. We're going to use the Visual C++ toolset, but you could use MinGW, you could use Clang on Windows. They'll do the same thing. It's just a different toolset. So we'll start by looking at this hello.cpp that we're going to use to build a DLL. Now, I know you're here at CppCon, you're excited for awesome advanced C++. This is not going to be it. This is about as advanced as the code that we're going to be showing in this talk because we're focusing on the DLL mechanism, not the C++ code. So here, this is just a very simple function called getGreeting. It returns a pointer to a string. The only non-standard thing we've had to do here is it has the cdecl calling convention. And the reason is that when you're talking across the DLL boundary, you want to make sure that everyone agrees on the calling convention since there's more than one. Otherwise, you'll end up corrupting your stack or breaking something. So all of our exports will be explicitly cdecl. You can pick a calling convention just as long as you use the same one on both sides. So we're going to take this, we're going to compile it. So cl/c compiles it, it does not link it. And so that'll produce hello.obj. On most of the future slides, I'm going to skip the compilation step because it's always the same. There's nothing special about that. And we're just going to show the linking step. So here is where we're going to produce the DLL. So we take the hello.obj file. We pass the DLL option to the linker, which tells it don't build an exe, which is the default, build a DLL. We say no entry. The only important thing right now is that basically reduces the amount of stuff that gets put into the DLL, which makes this example a lot simpler. And then we use /export to tell it getGreeting is part of the public interface of this DLL. So getGreeting is one of the things that you can actually use from outside of the DLL. And so if we run that, it'll actually, it says it created hello.lib. We'll talk about that in a bit. It also created hello.dll, though it didn't tell us that. So now that we have our DLL, we can just run it. No, we can't just run it. Sorry, that won't work. So we're going to have to write a program that actually uses this. So I've written a program called printGreeting. We have a main function in it. What we're going to do is we're going to call this load library function that basically finds the DLL, loads it into memory, and gives us a handle back called an H module that we can use to refer to the DLL that's been loaded in memory. So this will do that. We'll then create a function pointer type that matches the type of this function that we're exporting. And we're going to call getProcAddress for the getGreeting function. So we're going to ask the loader to give us the address of this function inside of that DLL. Reinterpret cast it to the appropriate type. We'll then just call puts to print the string out, and then free library because we're done using the DLL. And then finally, we need two headers because we are using functionality from std.io for puts and Windows for the various library loading functions. So then we can compile and link that, and then if we run the program, we see it prints out, hello C++ programmers. For those of you with a short attention span, that was the same string that we had in our DLL, so good, we've got it working. This is our example. All right. So let's take a look at what's actually inside of that hello.dll that we built. So when I want to look inside a file, there's a program called type, very helpful. So here's what's inside of the file. It's not particularly useful. I asked on Twitter, I told people I couldn't figure out is there a better tool for this? Someone suggested Notepad, so that works unfortunately just as well. We have some other tools we'll be looking at here. So a DLL file consists of basically a handful of things that are just in sequence in the file. So it starts off, every DLL has a DOS stub program in it. It's completely useless now, but it's there for legacy purposes from back when Windows and DOS interoperated. It then has a PE signature, which marks the beginning of the PE. The PE stands for portable executable, so every DLL and exe is one of these PE files. There's a big specification on the Microsoft documentation website that has all of the details I'm about to talk about. It then has a COFF file header, which has a little information about the file. It has an optional header that's not actually optional, that has DLL information in it. It then has a set of section headers that tell you how to find information in the DLL, like what's actually inside of it. And then it just has all of the code and data after that. So we'll start by looking at the DOS stub and the PE signature. So this is, I've opened it up in a hex editor. You can see it's a little stub program, or well, it's probably not easy to see that. But it basically just is, it's a little DOS program that prints out this program cannot be run in DOS mode, so that, back when DOS and Windows interoperated, if you ran a Windows program in DOS, it wouldn't, actually run. It would just print out this message. So then we can also see here, it's got the PE signature at the end. So there's the PE and 2 null terminators. How do we find that? There's basically a well-defined way. There's at offset 3C in the file, there's a value, and that tells you the offset of the PE signature. So it's at C8 in this file. All right, that's all just how we get to find the information we want to look for. So next up, we're going to look at the COF file header, the optional header, and the section headers. So to do that, we're going to use a tool called dumpbin, which basically just parses DLL or exe files, and it gives you all sorts of information about them. So it goes and parses all the data structures inside of them and presents it in a mostly readable text form. So here we've run dumpbin/headers, which prints out all of the header information. And at the top of those, we'll see that, okay, it's recognized that this is hello.dll. It's found the PE signature, which means it's at least starting to find that it's a valid file. It's discovered it's a DLL, and then it's going to print out the actual contents of the COF header. So we can see here it tells you what machine this is made for. So this is the kind of process the DLL has to be loaded into. It tells you that this DLL file has 2 sections in it, which we're going to need later when we go to look for the section headers. It tells you the time and date stamp that this DLL was built. This can actually be any value, so it's not necessarily the time and date stamp. It is by default, but you can customize that. It tells you the size of the optional header. And then it has some characteristics. So this file contains executable code. So executable here does not mean that it's an exe. It just means it can be loaded as an executable DLL. It says it can handle large addresses. This is a 64-bit binary. It has to be able to handle large addresses. 32-bit is different. And then it's a DLL, not an exe. So then what the loader will do is it'll look at that size of the optional header, and that will tell it the type to interpret the option to use to interpret the optional header. So there's 2 types of optional headers. There's PE32 and PE32+. And as you would guess, PE32 is for 32-bit binaries, and PE32+ is for 64-bit binaries. So you can see here there's also a magic number that allows the loader or the linker or the loader to make sure that it's parsing the right kind of data. We can see here the entry point is null. We'll talk about entry points later, but basically we told it no entry, so that's what we're expecting to see. It has the preferred base address for the image, which becomes important later. It has some alignment information. It tells us the size of the image is hex 3000 bytes. And it's got some characteristics, some extra information. And then finally, there's some directories, which are additional metadata about what's inside of the DLL. So you'll see that in the directories, it actually says RVA and size. So what is an RVA? And to talk about that, we have to talk about how we address within a DLL. So let's say you've got your program running. So we've got the heap there. We've got printgreeting.exe. We've got a couple thread stacks, some other data somewhere. And we want to go and load our hello.dll. Now our hello.dll wants to load at this base address. And the loader will say, all right, is that space free? Yes, great. It'll load it there, and it'll, everything works fine. Everything's happy. But what happens if, we've started a couple other threads, and they're now occupying that space in memory? It needs to go and put the DLL somewhere else. We can't load the DLL there. That memory is already in use. We'd go and overwrite something. We can't move data around in a native process because you've got just random pointers pointing to things. So maybe the loader will load it, up here instead. We'll talk a little bit more about this later in the talk. In general, DLLs actually don't get loaded at the preferred base address anymore. Basically, as a security feature, the loader will try to load them at a random address in each process, so it's not predictable where the data will be. But the important thing is that a DLL can be loaded at all sorts of different places in your address space. So we need a way to address things within a DLL without relying on the actual address at which it's loaded. And so what we use are what are called RVAs, or relative virtual addresses, which are just offsets from the beginning of the DLL. So if you want to find the address of something in memory and you have its RVA, you just add it to the base address at which the DLL was actually loaded. Or if you have the address of something and you want its RVA, you just subtract the base address from it. So for example, if our getGreeting function in hello.dll has an RVA of 2000, and if hello gets loaded at its preferred base address there, then getGreeting will be located at this address because, again, you just add the two together. So that's the optional header. The optional header then gets followed by the section headers, so they're just one after the other, and these tell you where to find the actual data inside of the DLL. So here, for example, is the first section. It's the text section, which contains code. We can see that because in the flags it has execute, and this needs to be mapped into a page in memory with execute and read privileges. We can see here the virtual address. So this is the RVA where this section will be located when the DLL is loaded. And then we can see the virtual size, which is the number of bytes that are actually contained here. There's only 8 bytes of code in this DLL. And then some other information about how it's laid out in the file. The second section is an RData section, which contains read-only data. We can see that in the flags here, that it will need to be mapped into a page that has read-only permissions, so not writable, not executable. And it's got slightly more data in it. From the optional header, we also saw that there were, those 2 directories. Well, this DLL had 2 directories. There are many more it could have had. And the RVAs there happen to be inside of this section. And we can tell that because the RVA of the export directory, for example, is 2040. And this section occupies all of the virtual addresses from 2000 up until 20D7. You can see that on the 3rd or 4th line of output. So from hello.dll's headers, we know that the DLL will occupy 3 pages in memory when loaded into the process. One page will contain the headers, one page will contain the text section, one page will contain that RData section, and we'll show that in a bit more detail in a bit. These aren't the only possible sections. There's other kinds of sections we might find in a DLL, but these are the only ones this program needs. The DLL has additional metadata in a pair of directories. There's the debug directory that we're not going to look at, but it basically has some very basic debug information. And there's an export directory that we will look at in a little bit. And all of that data is contained in the RData section because it's basically just read-only data that the loader is going to use. So then after that, basically we just have the sections. So the section headers told us where to find the data in the file. And so we can now look at what's actually inside of the sections. And to do that, we can use dump_bin/raw data, which will actually just print out the hex of the data that's inside of each section. So here we'll start with the text section. And we can see that, well, okay, it contains some bytes. Since this is executable code, we can also use the disasm option of dump_bin, which will actually disassemble it. And so we can see it's 2 instructions. All right, well, that's not very exciting, but there it is. We can then look at the RData section. And again, we can use the raw data option. And it's got, well, a bit more data. Most notably, it has our string there. So this is where the string is located. It's a string literal. It's read-only data. It'll be in the RData section. Additionally, those 2 directories that we talked about previously are also located in here. So I can highlight those. We're not going to talk about the raw bytes there. But we will look at what's inside of the export directory. So the export directory defines the public surface of the DLL. So it defines all of the things that other DLLs or XEs can use from this DLL. And so to get information out of it, there's an option of dump_bin. You just call dump_bin exports on the DLL. And here it'll print out, okay, we have one function that's exportable. So you can, if you have a handle to this DLL, you can call getProcAddress, and you can get this one function. That's the only thing that's available here. So at this point, we can put everything together. So in the export directory, we see, okay, the getGreeting function is located at RVA 1000. Well, I remember from previously, RVA 1000 is in the text section. And so we can disassemble the text section, and we can see, okay, that's the first instruction in there. Now, if you're familiar with, so that's pointing basically to that first instruction. Now, if you're familiar with x64 calling conventions and assembly, basically if you have a function that returns a pointer, like our getGreeting function, you put the pointer into the RAX register and then you return. And so here we can see that this is going to load the address of whatever is at RVA 2000 into the RAX register and then return. Well, what's at RVA 2000? Well, I remember that was inside of our RData section. And so if we look in there, that's at the very beginning of the RData section, and it's going to return the address of our string, or the address of our string literal. So that's kind of the basics of what's inside of the DLL, how all the pieces point at each other, work together. So in this example that we had previously of our print greeting, we saw how to link explicitly to the DLL. So where you actually call load library to get the handle to the DLL, you call getProcAddress to get the actual address of the function. But there's a little problem here. And that is that, well, load library is actually defined in a DLL itself, and getProcAddress is also defined in a DLL. So both of these are defined in kernel32.dll. So, well, we can't call load library to get kernel32 so that we can get the address of load library. That would not work. So DLLs can actually have implicit dependencies. So what you can do is you can run dump_bin dependence, which will tell you all of the dependencies that an XE or a DLL has. Our print greeting has dependency on kernel32.dll. And we can run dumpin/imports to find out what exactly it's importing from that DLL. And so here it'll say, all right, it has the following imports, and we can see free library, get proc address, and load library, which are the three functions that we called in our main function. And then it turns out, because we've statically linked the C runtime into this exe, so we can call puts, there's actually a whole bunch more imports. So I don't want to look at kernel32 for this because, again, there's so many functions and it's big and complex. So what I want to do is I want to convert this print greeting program that used explicit linking to our DLL, and I want to convert it into this one. So basically, we just want to declare our getGreeting function and then call it, and then use implicit linking to get everything to work. So what we're going to do is, again, we're going to, previously we linked our hello.dll, and that printed out creating library hello.lib. That library is an import library for hello.dll. And so what we can actually do, we can actually also run dump in exports on that lib, and it'll tell us, okay, well, the getGreeting function is available. So what's actually inside of there, you have to run dump in all to get more detailed information, and this prints out tons of stuff, so I'm just going to show the important excerpts. It has the two linkable symbols, so it has a getGreeting symbol that it can be linked to, and then it has an imp getGreeting. And then there's an extra member inside of the library that actually says, okay, this getGreeting function is a code export, so it's a function, not data, and it's located inside of hello.dll. So what happens inside the linker is this is as if the library had the following. So it's as if we had a function pointer of the correct type, and it's got a global variable, imp underscore getGreeting, that gets initialized to the address of the getGreeting function inside the other DLL. And that happens through magic. And we'll see how that magic works in an upcoming section. But for now, just assume that this ends up being the address of the getGreeting function. And then getGreeting is basically just a stub that gets statically linked into your program that calls through that function pointer. So this way, when inside of our main function, if we call getGreeting, it'll end up calling through that function pointer and getting the function from the DLL. So then if we have our print greeting implicit function or program, we can compile it, we can run it, and we get our message again. Then if we run dump in dependence on our print implicit program, as compared to our print greeting program, we can see, well, now it depends on hello.dll, just like the other one depended only on kernel32. And if we look at the imports, we can see, okay, it imports getGreeting, and we no longer import the load library, free library, and get proc address from kernel32, but we still do import all the things needed for the C standard library. All right. So far, we've looked at how you can use /export to tell the linker what you want your export service to be. There's a few other ways, and there's a few advanced things that we can do. So we'll look at that. So I'm kind of tired of this, silly example of, our greeting program. So I came up with a new example. I thought it'd be useful to have a DLL that has commonly used math constants. So to that, we're going to have these three functions now: get 1, 2, and 3. And so from previously, we know that we can just pass /export for each one of those, create the DLL, and then if we dump in the exports, we'll see, okay, it exports all three of those. So that's just the same as we were doing before, except now we have three of them. And if we look in the library, it also has all three of them. You can also rename exports. So for example, here, if instead of calling it get3, we wanted to call it get1 plus 2, we don't even need to rename the function inside of the code. We can leave it named get3. I don't know why we wouldn't want to change that, but it's possible. And then we can export it as get1 plus 2. And so then you see in the exports list and in the import library, it's just renamed the symbol, but in our code, it stayed the same. Now let's say we want to add get3 back. We can do that. And you can note in the exports list that we haven't added a new function to the DLL. We just added a new name for it in the export list. So here you can see get1 plus 2 and get3 are both at RVA 1020. You can also have private exports. So these are exports that you can call getProcAddress to get them, but they're not in the import library. So you can't implicitly link to them. You can only explicitly link to them. So this is useful, for example, if you want to deprecate some functionality. You don't want people calling something anymore, but you can't remove it because you've got people depending on the existing APIs. So this slash export can get very unwieldy if you've got like 1,000 exports from your DLL, right? Like you don't want to have to keep updating your make files every time you add new exports, and you don't want to have to maintain a gigantic list of these options. I expect you'd run up against some limit on the length of the command line eventually. So another option is you can use what's called a module definition file. So our numbers program is still the same as it was before, but now we have a new file called numbers.def. So this file just says this is a module definition file for numbers.dll. The DLL is implicit. And then it has the list of exports. So here we export the get1 function. We're going to export get2 as being private. And then we'll do the rename trick. I'm just doing this to show you the syntax of the different options. When we link, instead of passing /export, we pass /def to tell it what the module definition file is. And then if we run dump bin, everything is just as it was with the /export options. So this is basically just another way of specifying all of the exports for the DLL. There's another option that lets you do it inside of your code. You can annotate a function with declspec DLL export. And then we don't have to tell the linker anything. Basically, we just pass it the object file. And then if we dump in the exports, we see it's got all the exports. Magic. It turns out it's actually not magic. What happens is the compiler basically just injects into the object file some strings, and it tells the linker, pretend as if you got these on the command line. So basically, declspec DLL export just gets turned into these linker directives, and so it's exactly the same thing under the hood. Finally, there's a fourth option. I don't really know why one would use this, but it's a possibility. You can actually pass those directives using pragma comment. So there's this Visual C++ specific pragma that you can use, and so this will inject those directives into the object file just like the declspec DLL export did automatically. So if we do that, we can see the same exports. Cool. So now kind of the meat of the talk. What happens when we load hello.dll? So the loader has to do a lot of things, and there's a lot of advanced features that DLLs can use. There's a lot of interesting things they can do. We're not going to touch on most of those. We're going to focus on the things that are germane to our simple example here. So we're going to look at 5 steps, basically. So first, the loader needs to find hello.dll. It needs to map it into memory correctly. It needs to load any DLLs that our hello.dll depends on, any implicit dependencies that it has. It's going to bind imports from DLLs on which hello.dll depends, so it needs to actually go and initialize those function pointers like imp_getGreeting that we had. And then it needs to call the entry point for hello.dll to let it initialize itself. So before I get into all that, I just wanted to note, so DLLs are reference counted. So for example, here, if we call load library twice on hello.dll, the first time it will load the DLL and its ref count will be 1. If you call it again, the ref count will then just be incremented to 2. It's not going to load the DLL a second time. Both hello1 and hello2 will actually be the same. They'll be the same value, same handle. And then when we call free library on the first of those, it'll just decrement the ref count. It won't actually, free the unload the DLL. And then when we call free library a second time, it will then unload the DLL. All right, so the first thing we have to do is we have to find the right DLL to load. If we say load library hello.dll, how does the loader know where to find hello.dll? So the easy case is if we were to have passed it an absolute path. So here, instead of just calling load library hello.dll, we call load library a:\hello.dll. So if a:\hello.dll has already been loaded, the loader will just return its module handle, so that's easy, right? Again, it's going to be reference counted. Otherwise, the loader is actually just going to find that file on disk. If it's there, it'll load it. If not, it'll fail the load. Additionally to this, you can actually load different DLLs that have the same name from different paths. So here, if I have one on my A drive, one on my B drive, I guess I have 2 floppy drives on this laptop, then it would actually load both of those. Those would be different module handles, and you'd have 2 different, hello.dlls in memory. So then, after that, if we haven't passed it an absolute path, so here we've called load library for the absolute path hello.dll. It's gotten loaded. The second time we call load library on hello.dll with no path, the loader is going to say, is there already a DLL with that name loaded? In this case, yes. And so it's actually just going to return, it's going to say, I assume that's the DLL you're looking for, and I'm going to return the handle to that. So here, hello DLL1 and hello DLL2 are the same. And we saw previously, well, you can actually have two DLLs with the same name that are already loaded. In that case, the loader is just going to pick whichever DLL was loaded first. So in this case, our hello DLLX that was loaded with no path is the same as A, because that was the first of the two that we loaded. So then, okay, we say there's no DLL with the name we're looking for that's already been loaded. And the DLL needs to, or the loader needs to find the one we're looking for. So what it's going to ask first is it a known DLL? So there's a small set of operating system DLLs that are considered well known to the operating system. And if you call load library for them, or if you have a dependency on them, it's always going to load the operating system version of it. It's never going to do any of the other searching. And it's basically to prevent DLL hijacking. It's to prevent someone from putting a malicious DLL in and replacing some OS functionality with their own. So here, for example, if we try and load kernel32 or ntdll or ole32, these are all known DLLs, so they get loaded from the system directory every time. Whereas if we call load library on our hello.dll, the OS doesn't know what that is, and so the loader will continue with the search process. If you want to know what the set of known DLLs are, you can use, they're all listed in the registry. You can just look at this registry key. These are from my Windows 10 laptop. So after that, all right, so it's not already loaded into memory. We don't have an absolute path. It's not a known DLL. The loader needs to go and search for the DLL. So this is the standard search path. Basically, it's going to start by looking in the same directory that our application is located, so the A drive for my little test program here. It'll look in the system directory, which will be system32 for 32-bit programs. It'll be syswow64 for, or no, I've got that backwards. Anyway, it'll be one of those. It'll then look in the 16-bit system directory, which is just named system because, legacy. It'll then look in the current directory, so wherever you ran the program from. And then it'll go through the directories in your path environment variable. And basically, it searches these in that order. And as soon as it finds one, it'll say, that's the DLL I must be looking for. The current directory used to be searched first. That changed in Windows XP, so that's no longer the case. This search process, it turns out, is highly customizable. So there's DLL redirections, side-by-side components. The path obviously can be customized. It's an environment variable. There's an add DLL directory function. There's a whole bunch of flags you can pass to load library EX. Windows Store and Windows Universal applications are totally different in how they work. I'm not going to talk about all of those. I list them here so that, if you're curious about them, like all of those, you can search for them and find more information about them. All right, so the loader has found the DLL it's looking for. In our case, it was easy. It was just right next to the exe we were running. But it now needs to map that DLL into memory. So it's going to open up the DLL, and it's going to look at the header, and it's going to say, excellent, hello.dll occupies 3,000, or, well, hex 3,000. It's basically 12,000 bytes in memory. So I'm just going to, copy the whole file into memory. But hello.dll is only 2,048 bytes. And the reason for this is the DLL actually has different alignment in the file, where it has hex 200 byte alignment, and in memory, where it has hex 1,000 byte alignment. So in memory, it has to have 4,096 byte alignment, because that's the size of a page. And as we saw previously, in our hello.dll, we have a text section, we have an rdata section, and they have to have different protections, right? The text section needs to be have execute privileges, whereas the rdata section, you don't want to have execute privileges. So basically, each section has to be aligned to a page boundary in memory. In the file, though, it uses 512 byte alignment, and the reason is that's the fat sector size. So back when this was designed, that was the default. You can actually change that. There's a linker option to change the alignment, so you can make it smaller if you wanted, but the default is probably fine for most purposes. So sections have to be page aligned in memory. This is what I was saying previously, that the text section has different permissions on it than the rdata section, so they have to be on different pages. Additionally, we don't actually need to store everything in the file. So for example, let's say I have a version of our hello.dll called hello buffer, and I've just thrown an extra 1 megabyte global buffer inside of that DLL. Well, the DLL file is still only 2,048 bytes in size. If we look in the headers, we actually end up seeing that, okay, the DLL does have a larger image size, so when it gets mapped into memory, it does have that extra megabyte that it's going to take up. But then if we look in the data section, we see that the size of the raw data is 0, Because again, this is going to be 0 initialized, so the default 0 initialization that the loader is going to do of these pages is sufficient. We don't actually need to put any data in the file for this. So there's some benefit here that anything that's 0 initialized, we don't need a whole bunch of zeros inside of our file. So to map the DLL into memory, basically the loader needs to open the DLL file and figure out what the image size is, where all of the sections are located. It needs to allocate a contiguous page-aligned block of memory of that size. So all of these pages do have to be allocated contiguously, otherwise the relative virtual addresses don't work correctly. And it has to copy the contents of each section into the appropriate area of that block of memory. Later it will set the appropriate page protections on each page in the map DLL. Before it does that, there's a couple more things it has to do. So next up, it has to do relocation, potentially. So let's say we have another little DLL we're going to write. And in it, we've got two global variables. And I've exported them just so that we can get their addresses very easily in the next slides. So first, we've got a global variable named 2, which is just an integer with the value 2. And then we have a global pointer variable that just holds the address of that. And we link it. So how do these look in the DLL? Well, we can look at the exports. Again, this is why I exported them. And we can see that 2 is at RVA 1000 and the pointer is at RVA 1008. And so if we look at the RData section, we can see, okay, 2 is at RVA 1000 and pointer to 2 is at RVA 1008. And you can see that the pointer to 2 actually contains the actual pointer we're expecting to find it at. So it's assuming that the DLL is located at its preferred base address. So this is only going to work if pointerglobal.dll gets loaded at that preferred base address. If it gets loaded at, say, 90 million hex, then this won't work. Like that pointer will be pointing somewhere completely wrong. So what we do is we use, the DLL file has what are called relocations. And the relocations are basically a table of all of the pointers in the DLL that need to be fixed up if the DLL is loaded somewhere other than its preferred base address. So it's actually just a very simple table, so if you can dump in relocations to get the list of them. And basically, we have one here, and it just says that there is a pointer located 8 bytes from the start of the section beginning at RVA 1000. And the reason you get this kind of weird output is that the table is very compact, so they don't actually store the RVA, all of the data all together in one place in the DLL. And what the loader will do is it'll just update each pointer listed in the relocation table by subtracting the preferred base address and adding the actual base address. So for example here, it'll take the original pointer, it'll subtract the preferred base address, add the actual base address it was loaded, we're assuming it's loaded at that address, and that gives us the new pointer value which the loader will just write into that location in memory. The reason that the pointer contains the address it would have if the DLL is loaded at the preferred base address, like instead of just having, say, the RVA to start off with, is because a long time ago, DLLs would have the loader would try to load DLLs at their preferred base address. So, like, if that address was available, it would try to load the DLL there, and it would only fall back to relocating if it absolutely had to. So basically, it was more efficient to do that. Nowadays, though, there's a feature called ASLR, Address Space Layout Randomization, where basically the loader will always try and load the DLL at some other location so that attackers can't, predict where the C library is and, use C library functionality to produce exploits. All right, so now that we've relocated the DLL, all the pointers are patched up, we now need to load all of the dependencies and bind any imports. So if we look at the imports in our hello.dll, we see it doesn't have any. So that's, all right, we can't use hello.dll for this part. So let's add a new function to hello.dll that will give us a dependency. So we already had our getGreeting function that returns a narrow string. We can just add a getWideGreeting function that takes a buffer and it copies that into a wide character buffer instead. And I've done this because then we can call multi-byte to widechar, which we would have to import from kernel 32. So when we link it, we now just add the new export to the command line. We add kernel32.lib, so it links in, the import for that function that we're now calling. We look at its exports. We see, yes, we've got both functions. And we look at its imports, and we see, yes, now we're importing multi-byte to widechar. So this is for exposition. I just thought it was easier to show as, fake pseudocode. Basically, the loader is going to loop over all of the DLL dependencies. It's going to load each dependency. So it's going to, in this case, we've only got one. So it's going to go and load kernel 32, which will probably already be loaded in the process. If that fails, it'll return failure. So it'll actually fail to load your DLL as well. And then for each function that gets imported, it calls getProcAddress to go and get the actual procedure. Now, the loader internally doesn't actually call load library or getProcAddress, but this is conceptually exactly what the loader is going to do. So, or in English, basically the loader is going to load each DLL that we are dependent on, and then get all the required exports so that it can fill in those imp variables, those function pointers. All right, at this point, the DLL is basically loaded, almost ready for use. The loader now gives the DLL the opportunity to initialize itself if it needs to. And it does this through an entry point, which is conventionally called DLL main. So DLL main is a function that you implement in your program, and it's like the C main function, but for DLLs. So it takes 3 parameters. The instance is your actual DLL handle. So it's the same one that will be returned from load library if someone's loading you that way. The reason indicates why the function is being called. So there's 4 different times when the loader calls this function. It calls it on process attach, which is when the DLL gets loaded. It calls it on process detach, which is when the DLL gets unloaded. And then it calls it on thread attach and thread detach, which are when a thread starts or stops running within the process. And then the reserve parameter just gives a little extra information for some of those. And then you get the opportunity to return true on success or false on failure. If you return false, then your DLL fails to load. Finally, calls to DLL main are synchronized by a global lock called the loader lock. So basically, only one thread can be initializing a DLL at any one time. Not all DLLs have an entry point. So for example, our hello program, when we linked it, we said no entry, I don't want an entry point. And then if we look at the headers there, we saw there's a null pointer for the entry point. So there's no entry. So basically the loader will see that and it'll say, all right, you don't need to be initialized, I don't need to do anything special. So let's build a little DLL with an entry point. Here I have just a simple DLL main function that just prints out a message when it gets called for process attach or process detach and then returns true. And so when we compile that, we basically, instead of passing no entry, we pass /entry with the entry point that we want the loader to call. So we'll write a little test program to demonstrate it. And so here, basically, we just print out, I'm about to load the DLL. I load it. I then say, all right, I've loaded the DLL. I'm about to unload it. I call free library, and then I print out, all right, I've unloaded it. We link that, and then when we run it, we should see, all right, we're in the main function, about to load the DLL. We're now loading the DLL, so we're in DLL main for the process attach, which it prints out correctly. We're back in the main function. The DLL has completed loading. The DLL main gets called again when we call free library because it's going to free the DLL and unload it. And then we're back in main at the end of the program. So if you write entry points, you do have to be extremely careful. So MSDN has an article on dynamic link library best practices. The short version is do as little as possible as you have to, when your DLL gets loaded. Be very careful when calling into other DLLs from your entry point because they may not have been initialized themselves. And do not synchronize with other threads from your entry point because, again, the entry point is called but the loader lock held, and so you often end up with deadlocks if you try synchronizing with other threads. In general, in C and C++ programs, you won't specify your own entry point. We'll look at this in a little bit when we discuss C++ specific things. But instead, you'll let the C runtime provide the entry point, and you can define DLL with DLL main, which it will call. All right, so that's what it has to do in order to load a DLL. But what happens if something fails, something doesn't work correctly? How do you diagnose what went wrong, right? So load library is just going to return a null pointer and a status code. Like, how do you get more information? So I know this talk is early in the morning. If you've fallen asleep, now would be a good time to wake up because this is the most important thing I'm going to share with you today. I know a lot of people don't know about this, but it makes debugging this sort of thing so easy. So what I'm going to do is I'm going to delete hello.dll so that when we run our print greeting program, oh, well, it doesn't print anything out. And if we look at the error level, that happens to be the code for an access violation. And the reason for that is, well, it failed to load the DLL, and we didn't have any error programming in our test program. So it's just everything's failed. So how do we find out what went wrong? What we're going to do is the Windows debuggers package comes with this tool called gflags. So we're going to run gflags, and we're going to say that when our program runs, show loader snaps. So then if we open our program in the debugger, basically the loader is going to print out lots of information, basically all of the things that the loader is doing. So when it starts up, it's going to say, hey, I've just started, running this process, so it's going to just give you a little information. So here's what it's going to print when it tries to load hello.dll, which is going to fail. So it says, all right, I've started, I'm trying to load hello.dll. I'm going to see if it's a known DLL. It says, nope, it's not a known DLL, that's not it. So then it starts trying to search the search path, and it actually tells you the set of paths that it's going to try and search for this DLL. You'll notice this matches that search order that we were looking at earlier. It's the DLL in which our program is, it's the system32 directory, the system directory, the Windows directory, and so on until it gets to my path. Then it's going to try each of those. So it's going to say, all right, can I load a hello.dll? Nope, that failed. Can I load system32 hello.dll? Nope, that failed. And so on until it gets to the end. So this will actually tell you every step that the loader is going to try and do to load this DLL for you. So you can kind of see what went wrong, right? You can see, oh, the DLL, it wasn't in the right location, or I've got, my paths configured incorrectly. Whatever, this tells you exactly what the loader did, and you can compare that against what you were expecting it to do, and figure out what went wrong. Similarly, if we were to relink our hello program and we were to remove the export and then call getProc address to try and get that export, it'll print out a little warning that says, well, when you tried to call getProc address, it wasn't there. So this is how you can determine if a load fails because you were depending on an export that doesn't exist for some reason. This will tell you which exports were missing. And then when you're done, you just need to run gflags again with -SLS instead of +SLS to turn it off again. Now you're probably thinking, oh, cool, this is a great reason to use the Windows debuggers. And since I work on the debuggers team, I'd like to say that. But this actually works with any debugger. You have to run the gflags program separately, but then like in Visual Studio, the output will show up there as well. Basically the loader uses output debug string. All right, another little feature there is, inside of a, so we've already seen DeclSpec DLL export, which you can use inside of a source file so that the linker will know, all right, I'll just implicitly export this. This is, so I don't have to pass /export or things like that. There's also a DLL import. So you use this inside of programs that use a DLL. So what does this do? So first I'll look at a program that calls these imports without using DeclSpec DLL import. So here's just a simple program. Our main function calls get1. There's no DLL import. We link this program with the import library. And if we look at what the main function ends up doing, it's just a call get1 because it thinks, all right, this is just a function I need to call. And then get1 just jumps through that function pointer. So then if we use DLL import, it does things a little differently. Basically, this tells the compiler this function is going to be imported. So the compiler knows when it's generating code for the main function, it can just do the indirect call directly there. It can avoid that extra thunk through the get1 function stub that it had in that binary. You might think, all right, this is a great idea. Like we should definitely be using DLL import. Today, if you're using whole program optimization or link time code generation, the linker can see right through all of this, and so it will actually do this optimization for you even if you don't have the DeclSpec DLL import. So it's not entirely necessary today, obviously, in unoptimized builds, or if you're not using link time code generation, this would still be beneficial, but it's not really necessary if you're actually using all the optimizations you should be using. So we've seen exporting functions. You can also export data. So here, instead of exporting get1 and get2, we can export variables named 1 and 2. And to do that, you use exactly the same methods that we did for exporting functions, except you should add data after it, or in the def file, I think there's just no comma, you just say data. And then if we dump in exports, we see, great, we can see their RVAs, which point, as we'd expect, to, oh, well, there's a 1 and there's a 2 inside of our DLL. And if we want to write a program that uses these, so use constants, we can see we just declare the variables, we compile it, and oh, it doesn't link. That's interesting. So for when you import data, you actually have to use DeclSpec DLL import. And the reason is that the variables aren't exported directly. They have to be exported by address. The export table only knows about addresses. It doesn't know, what an int is. So it actually, when you export an int, it actually, what's in the export table is the address of that integer. So, if we're actually able to bind the name 1 to that address, like the types wouldn't match. You would think that that pointer is the integer. And then we can see we can use it. 1 is 1, 2 is 2. You can also get data exports using getProcAddress. But note that, again, this was what I was saying previously, the export is an int const star, it's not an int. Anyway, that all works just the same. You can also delay load DLLs. So here, if we have our DLL with entry point again, this is again, it just prints out when it gets called for process attach and detach. I'm running out of time, so I'm going to flip through this a little quickly. Actually, I'm just going to skip this section. And get to C++ and DLLs. So this is CppCon. I figured I should probably talk a little bit about C++ and DLLs. So first off, you can have global variables, global C++ variables in DLLs. But you have to use the default entry point. So basically, the CRT provides this entry point named DLL main CRT startup. If you provide your own DLL main, it will call that automatically. But the CRT entry point does a bunch of other things that are necessary in order to do C and C++ inside of your DLL. So during process attach, if you statically link the CRT, it'll go and initialize that. It initializes the security cookie and other runtime check support. It runs constructors for global variables. It initializes add-exit support within the DLL, and then it'll call your DLL main. Finally, during process detach, it calls add-exit registered functions. It runs destructors for global variables, and it'll shut down the CRT if necessary. And it also calls your DLL main there for process detach. I do want to note, so because all of this is done inside of the entry point, all of the rules that I mentioned for implementing your own DLL main also apply to any global variables that have constructors inside of your DLL. So, you can't synchronize from within a constructor of a global variable in a DLL because you'll end up deadlocking, or you'll probably end up deadlocking with the loader lock. You can also export C++ functions. So here's a little example. We can have 2 add functions, one that takes ints, one that takes doubles. We can link it, and we look at the exports, and we get 2 of them. I don't know how to demangle those in my head, so one of them is one, the other is the other. You can export C++ classes. So here we've got a class with a couple member functions. We can link it, and of course, classes aren't things that exist, in the DLL. All you actually have are all of the member functions that operate on the class. So when you export a class, it actually exports all of the member functions for it. So here we've got the get value and increment that our class has. We have the 2 constructors that our class has, and then the compiler has gone ahead for us and actually generated the copy and move constructor for us and exported those. So I have some advice for exporting C++ functions and classes. Don't. So on Windows, there's no standard C++ ABI, so you're very dependent on the compiler. There's no guarantee that if you throw an exception from one DLL and you catch it somewhere else, that it's guaranteed to work unless you're using the same runtime library. Basically, when you're exporting things from a DLL, you really want to make sure you're using a very stable ABI like C or COM or WinRT, the 3 that are very well defined on Windows. So DLLs can have threads and thread local storage. I'm not going to have time for that. And actually, I think I'm just going to get to the end so that we can take a few questions. So if people want to come to the microphones, I'll be happy to answer any questions, but no heckling. Yes?
Hi. I'd just like to know, is there a way to prevent reading string literals when you peek into your DLL?
From, pardon?
So string literals defined in your code get pretty much dumped into your DLL as is, and it's readable when you peek into them. Can you avoid that?
So obfuscation is?
I'm guessing.
So there are tools to obfuscate code inside of DLLs. There's a whole bunch of third-party tools that can do that, that will try and hide, what is actually going on under the cover. It'll go and, move code around and make it very difficult, just to disassemble it. But, at the end of the day, if the machine's going to execute it, it's got to be there in some form.
Okay.
So, yes?
Hello. I have a question. Is there any mechanism that different processes can share the text segment from a DLL, or that the data segment is shared like copy and write, like in System 5?
Yes. Yeah, so the question, well, I guess everyone heard the question because we're at the microphones. So yes, so what I said previously was that the loader will attempt to, with address space layout randomization, it will try and load each DLL at a different base address in each time the program's run. That's actually not entirely true. It will try and use a random base address, but it will try to, like for any given DLL, like our hello.dll, it will try to load it at the same base address in every process so that any read-only data and any text pages can be shared between the processes. So you end up using virtual address space in your process, but actual system memory, like that can all be shared. And that's very critical for things like kernel 32, which is going to be loaded into 200 processes. We don't want 200 copies of that sitting in memory. Additionally, any writable pages are marked copy on write. So basically, DLLs will share them until the first time they try to write to it, at which point the page gets copied. And all that happens behind the scenes in the memory manager. So you don't actually have to worry about that in your own code.
So this mechanism is only possible if they're not reloaded to a different address. They have to be on the same address.
Right.
I'm right?
Yeah, so the loader does try its best to put it at the same address.
Not, then it's not possible. In the other case, he do.
Then it'll load it at a different address in that process.
Okay, thanks.
Mm-hmm. Okay.
Hello.
Hi.
So if you were writing a library, would you recommend using DLL export or avoiding it?
Yeah, so if I was writing a library, would I recommend using DLL export? My preferred approach is to use the module definition file. And the reason for that is that you actually have like one place where your entire public contract of your DLL is defined, right? So you have one place, it's very easy to make sure that you aren't accidentally losing exports. So like, let's say that you have some things that are marked DLL export and you accidentally stop compiling that file, or maybe you purposefully stop compiling that file into your DLL, you probably just lost all of those exports from your DLL as well, so you've made a breaking change to your DLL. So the def file makes sure that that won't happen, because again, if those symbols aren't there, you'll actually get a link error. It'll say you've removed this symbol. So basically, if you want to maintain a stable contract for your DLL, using the def file is probably the safest approach.
Yeah, I was also thinking static linking versus DLL linking. So if you don't use DLL export, you're avoiding mismatches.
Yes. So specifically for the C runtime, it marks functions as DLL import in its header if you're using the DLL runtime. And so if you have shared static libraries that use that functionality, basically static libraries have to be recompiled with different flavors of the C runtime in order to link correctly, which is a big hassle. Yeah.
Hi, James. As you may know, I'm a bit concerned about portability, and my question is, do you think the standard should be something about loading and finding stuff into shared libraries? Because when you try to do that on Unix and then on Windows, it gets very messy very quick.
Yes. So yes, I do have an opinion on that, and the answer is no. I don't think the standard should standardize that because it's completely different on Linux and Windows. I mean, yes, they both have shared libraries. They both contain code and data that you can share. But the way that they work, the way that their contracts are defined for your libraries, the way that lifetime is handled, the way that add, exit, and globals are handled, they're all completely different. And so standardizing that, I think it's just too late. We can't go and change how Windows does it because, we've got 30 years of software, doing it one way. We can't go and change how POSIX does it because, again, same thing. So yeah, I don't really see any benefit of standardizing that. I see opportunity for libraries to help, paper over the differences, or C++ libraries, but I don't think that's a good fit for the standard.
Hi, James. I have a question about the one part you skipped over, delay loading. We are using it quite extensively, and I was wondering what's the rationale behind deciding that it's not going to be automatically unloaded when you unload the DL that delay loaded something.
Yes, that I actually don't know the answer to that question, but if you come chat with me afterwards, I can help find it.
Okay, thanks.
Yeah.
You skipped really fast over two parts that I'm interested in, but I'll only ask about one of them.
Okay.
Can you just repeat what happens if I've got a global variable and I initialize it and the the constructor or whatever it is calling something from a DLL, is that a deadlock or what happens? Does it fix it for me?
It depends. So some things are safe to call. So for example, a lot of the exports from kernel 32 to do initialization of like synchronization primitives, things like that are safe. Many of the C runtime APIs are safe to call. You just have to be extremely careful because if another program calls something that holds this lock that you might depend on, and then that in turn tries to load a library. And then, basically you can end up with lock order and versioning very easily. So you just have to be very careful with what you end up importing. Like if they're things from, or what you end up using as global variables. So if it's things from your own code, like maybe that something will be safe. But if it's not from your own code, you have to use extra care. So I know for Windows, basically there's a small set of functions from kernel 32 that are guaranteed to be safe. And then we say try not to call anything else.
Okay, so even if I'm not doing anything weird with these load library X, but even if I just stick to the standard C++ plus DLL import, I can still end up in a deadlock if I'm not careful. Okay.
Yep. Yes.
Hi, could you please elaborate on your advice not to export classes from DLLs? Because this is what hundreds and hundreds of software projects are doing, and it's very, very surprising to learn that it's not advised. Yeah, so this will have to be the last question, and then I can take more questions afterward. So basically the C++ ABI on Windows is not specified, right? So the compiler does what it does, and each major release of the compiler, they may make breaking changes. So I know there's been object layout changes in some versions of the compiler. There may have been name mangling changes. I don't know if there's any developer on the compiler here, but I don't want to say something false. But basically, any major release, they can change that. And so it's okay to export C++ things from a DLL, like if it's just your one application package that is going to end up using it, right? So like if you are using DLLs solely for componentization within your application, it's probably fine, to use C++ across the boundary as long as you make sure you're always recompiling everything with the same tool set, with the same options, to pass things across. If you're trying to build a reusable component, so something that, a library that someone might use in their own application, if you use C++ across that boundary, you basically need to make sure that whatever options you use to build your DLL, they're using also on their side. So you might have to distribute, many versions of your DLLs for different versions of the tool set. You might have to deliver different versions for different compile options. So the standard library has different layout for different types under some options. So debug and release don't have the same layout for all types. So as long as you control like the full set of things that are exporting the C++ exports and then importing them on the other side, it's safer. But if you have like reusable components, you definitely want to use some kind of stable ABI. All right. Well, thank you all for coming. Again, I'm happy to take questions. I'll be here all week.